Lesson: Case Studies of Reinforcement Learning in Cybersecurity. Reinforcement learning has emerged as a pivotal technology within the realm of cybersecurity, offering adaptive and intelligent solutions to counteract increasingly sophisticated cyber threats. By leveraging the principles of RL, cybersecurity systems can autonomously learn and evolve, enhancing their capacity to identify, mitigate, and respond to a myriad of cyber threats. This lesson explores the application of RL in cybersecurity through detailed case studies, demonstrating its potential and effectiveness in real-world scenarios. One significant application of RL in cybersecurity is in the development of intrusion detection systems. Traditional IDS rely on predefined signatures and patterns to detect malicious activities, which can be limiting when faced with novel or evolving threats. RL-based IDS, on the other hand, utilize machine learning algorithms to continuously learn from network traffic and adapt to new types of intrusions. A notable case study in this domain involves the use of RL for anomaly detection in network traffic. A research conducted by Sultana and Chilamkurti demonstrated the efficacy of RL in detecting network anomalies. The study employed a deep queue network to train the IDS, which resulted in a significant improvement in detection accuracy compared to traditional methods. The RL-based IDS was capable of identifying previously unseen attack patterns, reducing false positives, and improving overall network security. Similarly, RL has been applied to optimize the deployment and configuration of security measures in dynamic environments. In cloud computing, for instance, security configurations need to be continuously adjusted to protect against vulnerabilities and ensure compliance with security policies. An example of this application is seen in the work by Nguyen et al., where RL was used to automate the configuration of security settings in cloud environments. The study utilized a policy gradient method to train an RL agent that could dynamically adjust security configurations based on real-time assessment of threats and vulnerabilities. This approach not only enhanced the security posture of the cloud infrastructure, but also reduced the manual effort required to maintain security configurations, demonstrating the practical benefits of RL in managing complex cybersecurity tasks. Another compelling case study involves the use of RL for malware detection and mitigation. Traditional antivirus programs rely on signature-based detection, which can be easily circumvented by sophisticated malware that employs obfuscation and polymorphism techniques. RL offers a more robust approach by learning to detect and respond to malicious behaviors rather than specific signatures. A study by Anderson et al. Explored the use of RL in developing an adaptive malware detection system. The researchers employed a reinforcement learning framework to train a model that could dynamically identify and neutralize malware based on behavioral analysis. The RL-based system demonstrated superior performance in detecting and mitigating malware compared to conventional methods, highlighting the potential of RL in enhancing malware defense mechanisms. Cyber threat hunting is another area where RL has shown promising results. Threat hunting involves proactively searching for signs of malicious activities within an organization's network, often requiring significant expertise and manual effort. RL can automate and enhance this process by continuously learning from historical data and adapting to new threat landscapes. For instance, a study by Du et al. Applied RL to develop an intelligent threat hunting system that could autonomously identify and investigate suspicious activities. The system used a combination of supervised learning and reinforcement learning to build a model capable of detecting complex attack patterns. The results indicated that the RL-based threat hunting system was able to uncover hidden threats that had previously gone undetected, demonstrating the effectiveness of RL in enhancing proactive cybersecurity measures. Furthermore, RL has been utilized in the realm of automated penetration testing, where the goal is to identify and exploit vulnerabilities within a system to evaluate its security posture. Traditional penetration testing is a labor-intensive and time-consuming process, often limited by the tester's expertise and knowledge. RL can automate and optimize this process by training an agent to explore and exploit vulnerabilities autonomously. An example of this application is found in the work by Lee et al., who developed an RL-based framework for automated penetration testing. The framework utilized a deep reinforcement learning approach to train an agent that could adaptively discover and exploit security weaknesses in a simulated environment. The study demonstrated that the RL-based penetration testing agent was able to identify a broader range of vulnerabilities and generate more comprehensive security assessments compared to manual testing, underscoring the potential of RL in enhancing penetration testing methodologies. In conclusion, the application of reinforcement learning in cybersecurity presents a transformative approach to tackling modern cyber threats. Through various case studies, it is evident that RL can significantly enhance the capabilities of IDS, optimize security configurations, improve malware detection, facilitate proactive threat hunting, and automate penetration testing. By continuously learning and adapting to new threats, RL-based systems offer a dynamic and robust solution to the ever-evolving landscape of cybersecurity. These advancements underscore the importance of integrating RL into cybersecurity strategies, paving the way for more intelligent and resilient defense mechanisms.